Hello, my name is Dominique, and this summer I participated in the University of Arizona's Research Experience for Undergraduates program, where I worked on their CAT vehicle project, a student-led project where the goal is to create a fully autonomous vehicle, or AV, that can be used on the road. In this video, I'll be talking about the background of my project, the work on the car I ended up doing, as well as what direction my work can be taken into in the future. First, a little bit about me. I was born and raised in New Jersey, and I also attend school there. I go to the New Jersey Institute of Technology, or NJIT for short. I'm a fourth-year computer engineering major with a concentration on networking. This also wasn't my first time doing research. I've worked as an undergraduate research assistant for various professors at NJIT, as well as working as an REU intern last summer at the University of Southern California's Institute for Creative Technologies under the mentorship of David Traum. Before I get into the specifics of my project, here's some background to it. One of the most important features of an autonomous vehicle is its ability to interact with the environment around it. Interaction comes in the form of sending messages about whatever the car feels is necessary, which should range from anything to sending information about its location in the event of emergency, or warning other cars about an accident. Essentially, the information that the car will send can be classified into two categories: to other cars, which is called vehicle-to-vehicle communication, or to sensors embedded in devices around the car, which is called vehicle-to-infrastructure communication. An ideal environment is one where a given autonomous vehicle can both send and receive messages with the world around it, which would improve the efficiency and safety of the roads in the future. However, there are some obstacles blocking us from reaching this autonomous vehicle utopia. You see, in order to send and receive messages, AVs must utilize the spectrum space and frequency bands that are used for all telecommunications. The issue with this is that at times this space is being occupied by mobile phone users, which can cause interference if both devices try to use the same frequency bands to send their messages at the same time. The question of who gets priority is now brought up, which in this case would go to the mobile phone user. Devices such as phones are classified as primary users, or PUs, and devices such as AVs are classified as secondary users, or SUs. Here's where the idea of my project, Cognitive Radio, comes into play. Cognitive radio can be defined as a software-defined radio communication system that gives SUs the ability to find and use parts of the spectrum that aren't being used by PUs, which in this case allows AVs to send messages without worrying about interference. A lot of progress has been made with cognitive radios in the last couple of years, and most of this is due to the rise of artificial intelligence, specifically reinforcement learning. Reinforcement learning is a branch of AI that involves setting up an agent and an environment that the agent can interact with. The agent is given states that can exist within a set of actions that can execute also within those given states. The goal of any agent in a reinforcement learning environment is to learn a sequence of actions that will allow it to navigate its environment successfully, with success being defined by the creator of an environment. Reinforcement learning in the context of cognitive radio involves training a cognitive radio with some type of positive reward for making the correct actions in a given state and a penalty for an incorrect action. Some popular problems that reinforcement learning enabled cognitive radios are being applied to are spectrum sensing, dynamic channel selection, and energy detection. For my project, I decided to focus on energy detection. The overall goal given to me by my mentors was to begin the foundations of a cognitive radio Python package that eventually would be used by the CAT vehicle so that I could communicate efficiently with the world around it. There already do exist packages that can simulate cognitive radio, but none of them are written entirely in Python, and at times they can be difficult to set up. My package would be unique in the fact that it was simple to install and use, and could be extended for any simulations that a user wrote for it. My Python package was mainly centered around three files: an MPSK file, an agent file, and an environment file. My MPSK file is used to simulate the process of sending bits. To do this, I wrote Python functions that can modulate an array of bits using PSK modulation, turn them into an analog signal, add random noise to them, turn them back into a digital signal, and then finally demodulate them. I also wrote a function that allows a user to measure the bit error rate of a signal that they create, so that they know how many errors to expect in a signal that they send using my functions. In my agent file, I wrote two reinforcement learning algorithms I can use to explore the environment in my environment file: a Q-learning algorithm and an upper confidence bound, or UCB, algorithm. Finally, the environment file. It uses the features of the MPSK file to generate 5 test signals, which make up the environment that the agent tries to send messages in. These files combine to make up an ideal cognitive radio situation. Given the amount of energy of each signal, the agent must decide whether or not to attempt to send a message on that channel. Future REU students and researchers can add to the files that I have now by adding more modulation schemes, more reinforcement learning algorithms, and more simulation environments. I was able to create a foundation that can be used by future REU students, but there's still work to be done on my end. After I finish this REU program, I plan on expanding the functionality of my Python package, as well as writing the documentation for it. In addition, I want to write 2 papers, one that explains how to implement my code and why it's relevant to cognitive radio research, and another that analyzes the performance of my reinforcement learning algorithms in the environment that I created. To close, I'd like to thank my mentors Noel Teku and Raul Badani, for all the insight and advice they gave me in creating and finishing this project, as well as the program coordinator Nancy Emtaj for making things run so smoothly this summer. Overall, this REU experience has helped me to prepare for the type of research that I'd like to do in graduate school, while also being a fun and cool location that I enjoyed being in. I highly recommend to any undergraduates that are serious about doing research to do this program, because of how much time and effort is put into making this program a success. Thank you.